My talk is about the representation of the stable boundary layer in AROME-Arctic, and especially on the role that stability regimes can play in that representation. I'm focusing on a period during YOPP SOP-NH1 around the supersite of Sodankylä. So probably, as you know, AROME-Arctic is the operational weather prediction system employed by Met Norway for the European Arctic. And here on the side, we can actually see the forecast errors that are encountered by the systems of Met Norway along the coast. And as you can see in general, that the forecast errors grows the more north we come. And one of the reasons as to why that is the more important role that the stable boundary layer plays at higher latitude, which is why we focus on that here. So if we think about the representation of the stable boundary layer in NWP models, we often encounter the warm bias in high latitudes, which you can see here in red shading. So what you look at here is a time series doing YOPP SOP-NH1 taken at the Sodankylä mast, and you can see the observations in the black dashed lines showing these very distinct drops during the nocturnal periods. And the model doesn't really catch up with that. We can see the modeled temperature evolution in the black solid line, and we can see that because it doesn't capture this drop, it actually leads to this strong warm bias by the end of the night, which here can account for like 6 to 8 Kelvin. However, this warm bias, and thereby also the representation of the stable boundary layer, can actually change on small spatial scales. And during YOPP SOP-NH1, that happened in AROME-Arctic. So there on the side, you can see a zoom in of the domain around Sodankylä, and the mast location is shown by the X. And now we take two grid boxes, which are essentially neighbors, called A and B here, and they show very different representations, which is shown here in the panels A and B. So A is the one we just looked at. We have the strong warm bias emerging, but in the B case, actually we see a much better performance, especially in the second night, where the development in the model is captured much better what the observations are seeing, and the warm bias is reduced by 2 to 3 Kelvin. Even though I don't show it here, you can rest assured that the surface conditions of these 2 points are actually very similar. They have the same roughness lengths, snow area fractions, snow depth, and vegetation cover. So it's not the surface that is different here, but it's actually the representation of turbulence in the boundary layer. Because we know that in the stable boundary layer, we can have these contrasts on small spatial scales, and they are often connected to different stability regimes. So if we talk about the stable boundary layer, we usually have to distinguish at least between the weakly stable boundary layer and the very stable boundary layer, because they actually refer to very different feedback mechanisms between stratification and turbulence. So I tried to show that here with a little schematic in the middle. Okay, let's talk about the weakly stable case first. Let's say we have a cloud-free night, which means we have radiative cooling, stratification increases near the surface. If turbulence is maintained, let's say we have wind shear or wind speed, that means that the impact of the turbulent transport is also increased because displaced particles are going to bring a larger temperature deviation. So when that happens, it also means that turbulence starts to counteract the increase of stratification near the surface. And then what leads to, in the end, is going to be these very coupled profiles which give us like near neutral temperature gradients in the stable boundary layer throughout the night. In the very stable case, shown here in cyan, we have like the opposite feedback. There we actually find that turbulence decreases as a response to enhanced stratification, which means that the turbulence transport cannot counteract the stratification due to the cooling, and we end up with these very stable profiles near the surface. And it becomes clear that for weather forecast, it is very important that our models are able to represent these regimes. And not only that, it also needs to introduce these two types at the correct time and space for meaningful model forecast. And that was kind of the question of this study, like how does AROME-Arctic represent these regimes? Is it able to represent them? So are the physical schemes of the model able to represent these two regimes? And if yes, where does it introduce them? And especially for the first question, we need to look at the physical calculations that our model is doing, and therefore we are using a combination of two diagnostics. The first is called the individual tendency output, and the second one is called DDH. So the individual tendency output just opens up the model calculation, basically, looks at the contribution that the different components are doing, let's say the model dynamics or the model physics, and then forwards these contributions to the model output so we can actually investigate them and know what turbulence has been doing throughout the night. For example, here on top, you can see an example for model level doing the dry stable boundary layer, for example, and you can see that temperature can change due to advection, subsidence, radiation, or turbulence. The latter two, for example, being represented by physical schemes, the first two by the dynamical core. But we also know that processes in the stable boundary layer can be short-lived or intermittent. And if we think about our NWP models, we have like hourly output and sometimes 3-hourly output. And that might not be sufficient to actually capture these development that happened on shorter timescales. And therefore, we're going to use the second diagnostic called DDH, which is short for Diagnostic on Horizontal Domains, which is very nice because it allows us to define a region of interest, which in our case is going to be around Sodankylä. And then this diagnostic is going to create model time step output for every model grid point in that area. And then we can actually forward these tendencies to this high resolution output, and then we get detailed insight into the computation of the model, which allows us then to decipher the computations during the stable boundary layer. This is what we are going to use to investigate AROME-Arctic. So for a case study, as I said before, we are looking at a period during YOPP SOP-NH1 in March 2018, where most of Scandinavia was dominated by a large high-pressure system, which then led to like cloud-free conditions throughout days and nights. And especially in the nights, we then find that these very stable boundary layers occurred over Sodankylä, which you can see were observed at the mast again, shown by the red dot, with these very distinct drops in the nocturnal periods. And these drops were also affiliated with relatively low wind speeds, which are very favorable for these very stable conditions to occur. But we saw before that these drops, when it comes to the representation, it can change in AROME-Arctic on small spatial scales. So before we went into the, to look at how does the model represent that on the physical scale, we would like to know, are there like distinct patterns that we need to account for, or where do these regimes actually occur? And we can indeed find them, which we can see here. So this is the region that we had the high resolution output being generated for during the model run. And you can see at A, you can see surface temperature, then temperature at the lowermost model level, wind speed at the lowermost model level, and temperature difference between the two lowermost model levels. And you can see that all of these fields exhibit clear spatial patterns, which are actually collocated to different stability regimes, which is shown by the black contour. In the interior of the contour, you can find the very stable case, and in the outerior, you can find the weakly stable case. And now you can also see the difference. So the very stable case is affiliated with colder surface and near surface temperatures, weak wind speeds, and pronounced inversion strength. Whereas the weakly stable case is affiliated with warmer temperatures, stronger wind speeds, and an absence of the inversion strength. And you can also see the small spatial scales and the importance of that, because in this particular case, you can see again the measurement site or the mass in Sodankylä with the X, and the stability regimes are basically directly located on the border. And the two black dots we see there are the 2 points we compared before, showing us that these small spatial scales can be very important when we, for example, do validation studies or just forecasts. But of course, also it would be nice to know as to is there a particular trigger that causes these regimes to be at this specific point in time and place. And even though it's a bit tricky to fully decipher that, we can show the most important factors when we zoom out a bit. So that's the same area, just a larger perspective. A slightly different case, don't worry about that. You still see the small scales in which the two regimes occur, for example, with the cold temperature and the warmer temperatures. And we can now see that they are closely collocated to the topography, where the very stable case actually occurs in the lee of topography, and the weakly stable case occurs in the windward side or on top of topography, because at least in AROME-Arctic, those are affiliated with stronger wind speeds and weaker wind speeds. So we can kind of know, given the topography and wind direction, we kind of can know where this regime can occur. So now that we can distinguish them spatially, it would be very nice to know about the computation that the model is doing. So we group all the grid boxes that belong to the weakly stable case, the very stable case, and look at the mean development of temperature, and also the contribution that the different schemes are doing. So what we are doing for that is we take the high resolution output and then integrate the contribution by the turbulence scheme and the radiation scheme, and then we get the temperature development due to that process. And this is then how it looks like. We can see the mean or average developments in the weakly stable case and the very stable case. And we can start by the black solid line, which gives you the average temperature development, and you can see that in the weakly stable case, this is a drop of about 7 Kelvin in the night. And in the very stable case, this drop is strongly enhanced, showing us over 10 Kelvin in the night. And as to why that is, we can look at the role that turbulence plays throughout the night. And turbulence is shown by the orange dashed line. So what you can see in the weakly stable case is that the lowermost model level starts to cool at the beginning of the night due to turbulence. But then this cooling is diminished relatively quickly, so it diminished in strength. And at some point, it actually stops and transitions to a warming. And that is interesting, because if we think about turbulence at the low-mass model level, what it can do, it can lose heat to the surface, that would be cooling, but it can also gain heat from the higher model levels above it when there is an efficient coupling, because then they would transport heat downward the gradient, warming the low-mass model level. And that is what we can see happening in the weakly stable case. In the very stable, that does not happen. We can see that the orange line continuously drops, meaning that the low-mass model level continuously loses heat to the surface and doesn't gain any heat from the higher levels, telling us that there might be a decoupling going on in the model, that the low-mass level is now decoupled and is like basically cut off from this heat transport. And we can actually see that when we look at the vertical structure of the turbulence tendency, where in the weakly stable case, we can see this coupling where the higher model levels in the stable boundary layer cool due to turbulence as they efficiently transport heat downward to the surface to counteract the cooling to the surface. And we can see that here in the lowermost model levels, we actually have a warming by turbulence. In the very stable case, that does not happen. We can see that the turbulent transport in general is actually reduced, and the lowermost model level does not get any of that heat transport because it is decoupled and just constantly loses heat to the surface. And this is why we see this very strong cooling. So to conclude, AROME-Arctic is able to represent these two stability regimes. That is nice, and it also introduces them on very small scales, which is going to be important. When it comes to the representation of these two regimes, AROME-Arctic also does a relatively good job when we think back about this concept of the different feedbacks. As we see, like a nicely well-coupled boundary layer in the weakly stable case, and we see a reduction of turbulence and a decoupling in this sense of the lowermost model level in the very stable case. But now if you think about these small scales, it's important to consider that for model forecast validations or model development studies, because, for example, in this case, if we compare the location of the mass to the closest grid box, we can end up with disproportionately large model biases, because this grid box might have been in the wrong stability regime, which emerged during the model computation, which is important here. It's not like hard-coded, is actually emerging due to the physics. And if we take like a grid box which is basically next to that one, we find a much better performance. And similarly, it's also important for model development studies because these two feedback mechanisms can react much, much different to a change of the model physics, for example. And that is not shown here, but it's actually the teaser for the paper which is currently in boundary layer metrology and hopefully going to be published soon. Thank you very much.
So thank you very much. Are there questions for Marvin?
This is maybe in your teaser, but sometimes increasing the vertical resolution in these very stable boundary layer cases can improve or reduce the biases and improve the model. So I don't know if that's something you've looked at and whether you want to comment on that or...
Yes, thank you. That's a great question. Indeed, we actually have looked at that. That's a follow-up study to this one. So what happened is that what happened is that the boundary layer reduces in depth that we saw, and the gradients become stronger. But for example, the cooling near the surface was not affected, because what you saw with the lowermost model level being decoupled, what happened with higher vertical resolution is that a similar deep layer became decoupled, which now consisted out of 2 to 3 layers. So that characteristic was actually not changed. But it's indeed something we have to look into because we're going to a higher resolution.
Any more questions?
Yeah, great talk, Marvin. Glad we hired you. No regrets. Yeah, to follow a bit on resolution, not per se perhaps, but most of the things are one-dimensional. So you clearly identify this rather sharp the transition between weakly and very stable boundary layers. How important is it to go to more like three-dimensional description of turbulence, and how do you think that will affect your results? I mean, now you're one-dimensional, right? So if it starts to go like...
Yes, that is true. So probably like allowing turbulence to not only act in the vertical in the column, but actually to allow it to like look more left and right, or to like adjacent grid boxes might be a solution, or might be a better representation. Because right now what we can see, or what we can infer from our study, is that what dictates whether these regimes occur is always the model dynamics. It's always the dynamics, because the physics can just react, and either it's going to be locked in the very stable case, or it's going to be in the weakly stable case. So yeah, actually, if we would have a scheme that allows but then again, we have a lot of diffusion, so probably we should have checked that before. Probably it's better to use like an advanced turbulence scheme that either has a stochastic length scale that can give a kick of mixing at some point to like on its own get out of this, or to use like more sophisticated turbulence closures. But yeah, probably is a good thing to look at.
Okay, thank you very much.